Welcome to videos on summary of linear integrated circuits. In the second part of this summary of ICs, we shall see the applications of triple timer and op-amps. So, a stable multivibrator can be used as an voltage control oscillator. It is necessary that this VTH, that is the control voltage, if it is controlled by an external power supply, so we can change the oscillations by as per our wish. So this is the voltage which will change the oscillations of this stable multivibrator. So that's why this is called as VCO, as oscillations can be controlled using the voltage at VTH. Now we know that the capacitor will be always charging towards VTH. So if I change the VTH itself from 2/3 VCC to some external voltage, so we know that VTL is always equal to half of VTH, then VTL will be half of V external voltage. So we know the capacitor expression is given by Vf minus V initial into e power minus T by Rc. Now initial voltage VTL is now not 2/3 VCC, it's actually half of external. The final voltage is VCC, and at T is equal to TH, the capacitor will reach up to VTH. Here VTH is not 2/3 VCC, it's actually V external. By substituting all these parameters, we'll get on time as this expression, that is Ra plus Rb into C is the time constant multiplied by this constant term here. You can see there is a V external term coming here. Since V external is there as a part of your on time, the VCO, that is the particular circuit, by applying an external voltage of VTH, we can change the on time by changing the V external. So that's why it is called as voltage controlled oscillator. It is interesting to see what happens to the off time. So off time, so from the same expression, so with the initial voltage as V external, because when we are actually trying to find the off time, the initial voltage of the capacitor is VTH, which is V external. The final voltage is 0, that is, as capacitor is allowed to discharge up to infinite time, it will reach 0 volt. And at T is equal to TL, the capacitor voltage will reach half of the V external, that is VTL. Substituting all these parameters, it is surprising to see the T off happens to be the same as before without using that external voltage. It is 0.69 Rb into C, meaning if we change the external voltage, that is, if we change the threshold voltage VTH, that is higher threshold voltage, only the on time changes, off time remains the constant. Even if on time changes, we know that the total time and the frequency of the circuit will change. So it is possible to get required frequencies by changing the threshold voltage. So that is VTH. So it is also interesting to see, by varying the VTH, we can able to get any duty cycle, even the duty cycle less than 50% also, even for this circuit. So even, of course, in the previous video we have seen that to have a less than 50% duty cycle, we need to have a diode bypassing the RB, that is without changing that VTH. VTH was 2/3 VCC. Suppose the same circuit having RA and RB, if we change the value of VTH, it is still possible to get any duty cycle. That purely depends on what is the VTH that you applied. And since we can change the pulse width of the on time, that is on time width in a stable multivibrator, it can be used as a pulse width modulator. That is, a stable multivibrator can be used as a pulse width modulator. So here we are assumed the value of R and RB is equal to 1 kilo ohms and C is equal to 0.1 microfarad. It results in the on time of 138 microsecond and off time of almost half of that. Because this is the case when there is no external voltage applied, that is VTH is 2/3 VCC. Instead of having 2/3 VCC, always suppose if we apply a sine wave of larger amplitude, of course it should be centered around half of the VCC. suppose assume that now we should always ensure that at least there should be minimum of 20 pulses in one cycle of the sine wave. Since here, suppose if I take 4 millisecond as the sine wave frequency, this is going to be 4 millisecond as the time period, which will result in a 250 hertz sine wave. If I apply a 50 hertz sine wave of 4 millisecond time period, will at least accommodate around 20 pulses. If we have more and more pulses within one cycle, we can clearly observe the width variation. So width will keep on increasing during the positive uh, half cycle. So width is keep on reducing during the negative half cycle of the sine wave. Now when I say width is increasing, only the on time is increasing, the off time remains the same throughout the entire sine wave cycle. So I think you have already observed this in the videos, the previous videos, and also you have done the experiment to demonstrate the PWM generation using Astable Multivibrator. Now we should move on to the applications of op-amp. So this is an inverting Schmitt trigger. You can see here the op-amp is provided with a positive feedback. We all know that with positive feedback provided to the op-amp, the output voltage, the expected output voltage will be always plus Vsat or minus Vsat, depending on whether V plus is greater than V minus or whether it is V minus is greater than V plus. And of course, we have used resistors R1 and R2 for the feedback. R2 is the feedback resistor which is connected to output in the input. So R1 is the reference now. So we actually represent a parameter, a term beta, which is nothing but R1 divided by R1 plus R2. So as you can see here from the transfer characteristics of this, suppose if we apply input voltage whose amplitude is less than VTH, which is given by plus Vsat into R1 by R1 plus R2, which is given by plus beta VCC. Suppose if the input voltage is less than VTH, output always remains at plus Vsat. If the input exceeds this VTH, as you can see here, this is the input connected to the inverting terminal. The input exceeds the VTH value, so V minus becomes more than V plus, then output takes the transition from plus Vsat to, so it will make a transition from plus Vsat to minus Vsat, so as the input voltage exceeds VTH. Okay, suppose once it has reached minus Vsat, suppose if the input voltage for the output to make a transition from minus Vsat to plus Vsat, the input has to go below VTL. So if it is above VTL, it always remains in minus Vsat. If the input goes below VTL, then only it makes the transition from minus Vsat to plus Vsat. So that minus VTL is given by minus VCC R1 by R1 plus R2, which is minus beta VCC. Now what we are supposed to see here is that always the VTL and VTH magnitudes are same. If this is 4 volt, this is minus 4 volt. If it is 2 volt, this is minus 2 volts. And using this circuit, we can obtain any VTH, VTL. Of course, if VTH is 5, this is minus 5. So, but it is unfortunately you cannot get these two of different magnitude. So that can be obtained using the other circuit. Main important thing is that for the output to make a transition from plus to minus Vsat or minus Vsat plus Vsat, input has to exceed VTH and VTL values. We should see the modified circuit of this inverting Schmitt trigger, where we have this reference voltage applied. So this reference voltage will actually help us in getting any required value of VTL, VTH. So both VTL, VTH can be both positive, both negative. They can have different magnitudes. The beta is again given by the same value. So we can actually find the expression for VTL as minus Vsat beta plus V reference into 1 minus beta. So we have discussed this in the previous videos in detail, how do we get the expression for VTL and VTH. Suppose if I subtract VTH from VTL from VTH, that is VTH minus VTL, we call it as hysteresis voltage. So by doing that, we'll get 2 times beta Vsat. Suppose if we add those two, we'll get 1 minus beta times 2V reference. So we can actually design the Schmitt trigger for given specifications, and of course, since we have only two equations and two unknowns, we need to assume a particular value of resistor so that we can estimate the other two values. So this is the non-inverting Schmitt trigger, so where the input is applied to the non-inverting terminal. Still again, now you can see the positive feedback is given. The output voltage is either plus VSAT or minus VSAT. Now in this particular case, if the input voltage exceeds VTH, output makes a transition from minus VSAT to plus VSAT. If the input voltage goes below VTL, it goes from plus VSAT to minus VSAT. So this is VTH and VTL. It is interesting to observe that this VTH is given by plus VSAT, that is plus VCC R1 by R2. So we know that this VTH can never be more than VCC. So therefore R1 cannot be greater than R2. So always make sure that VTH is always less than VSAT or VCC. So therefore R1 should be always less than R2. If R1 is less than R2, we are ensuring that VTH is always less than VCC, so that it can make a transition from minus to plus and plus to minus. So this is a modified circuit to have different magnitudes of VTL, VTH, both positive, both negative, and it can be of different magnitudes. We are using a reference voltage here. So the expression for the same VTL, VTH will be now modified to this. So this is the original expression. We have plus one more term added. This is due to the application of the reference voltage. So as we discussed in the inverting Schmitt trigger, so you can actually design for a given VTL, VTH and the plus VSAT minus VSAT. You have to assume one resistor and we'll get the other resistor in the reference voltage. So this way we can comfortably design this inverting and non-inverting Schmitt triggers for any desired VTL and VTH. So again, VTL, VTH are the lower threshold voltage and higher threshold voltage for the output to make a transition. Please keep in mind that the input voltage should be always greater than the greatest magnitude of VTL or VTH. The input should be always more than the magnitude of VTL or VTH, whichever is more. Now we shall have a look at this astable multivibrator using op amp. So as you can see, conceptually we need to have a Schmitt trigger and a RC network which can make the capacitor charge and discharge to resistor R. Now this is the actual circuit for astable multivibrator. We have an inverting Schmitt trigger. We have R1, R2 used for feedback, and this capacitor is used to charge the capacitor. As the capacitor voltage charges above V plus or goes below V plus, so we won't have the output making a transition from plus VSAT to minus VSAT. That's what we are seeing here. When the output is plus VSAT, the capacitor is now charging with a time constant R into C. If it tries to go above beta VSAT, this is actually beta L plus. So L plus is this level, that is plus VSAT. Now capacitor voltage is swinging between plus beta VSAT and minus beta VSAT. If it tries to go above plus beta VSAT, the output makes a transition from plus to minus. If it tries to go below minus beta VSAT, it makes a transition from minus VSAT to plus VSAT. See, when it is trying to go below this, the output is going from minus VSAT to plus VSAT. So using this time constant R and C, we can able to design any desired oscillations. It is interesting to see both while charging and the capacitor charges to plus VSAT and capacitor also discharges to minus VSAT. The charging and discharging part is the same resistor R. So that's why this is what is the summary of all those. Now you can see now it is keep on charging and it goes above that at pin number at the position 2 it goes from plus VSAT to minus VSAT. Here it is keep on discharging. It makes the transition from minus VSAT to plus VSAT. So capacitor is always charging through R and R, and this time constant is RC. This can be, of course, we can actually get the expression for on time and off time, which is given by RC ln of 1 plus beta by 1 minus beta.